All right, welcome back to Unit 1, Exploring One Variable Data. Today we're going to look at topic 1.10, 1.10 on the normal distribution. And now this is going to be part 1. This is kind of a longer topic. There's a lot of conceptual stuff to explain, and then there's a decent amount of math work as well to do within this. So we're going to make sure that we call this part 1. And then there will be a part 2 video as well. All right, so remember the normal distribution. The normal distribution can be used to represent some population distributions. You know, we just spent 9 topics talking about distributions of data. Well, the normal distribution is just a very famous distribution that can be used to represent populations. So let's make sure we get a couple things straight here. Now, a statistic is a numerical summary of a sample. A number that describes something about that sample. We talked about mean, median, IQR, range, standard deviation, all that fun stuff. But the most important thing is to be a statistic, you have to come from a sample. Well, a parameter is a numerical summary of a population. It is a number that describes something about that population. So statistics are to samples are what parameters are to populations. It's actually really easy to remember. Statistics and samples both begin with S. Parameters and populations both begin with P. So they are very, very similar. Statistics and parameters are pretty much the exact same thing, but it's where they come from that makes them either a statistic, if it's coming from a sample, or if it's used to describe a huge overall population, then it's a parameter. So let's dive into those a little bit more. Statistics are real, right? They come from actual samples, sets of data. You can make a histogram from an actual set of data. So you can actually make a graph of your sample. And anything you get from that sample is called statistics. And the 3 most famous statistics, now there's many more, but these are 3 I consider the most famous, is the mean of your sample. We call that X bar. The standard deviation of your sample, we just call that S. And a sample proportion. This would be p hat. Like in your sample, 20% of people scored above a 50. Or in your sample, 18% of people scored below a 30. Something like that. It's a sample proportion, right? P hat. Or you could also use a categorical variable there and say, hey, 92% of people love chocolate milk. And that would be a p hat. Now, when we're working with parameters, they're theoretical. They are theoretical values that describe a population found from lots of research, right? You know, populations are huge. There's no way that to find the average weight of a humpback whale, there's no way we actually measured every humpback whale in the entire world, the entire population of humpback whales, and divided by how many there were to get the mean, right? It's theoretical. It's something that we learn and gather from lots of research. So because we cannot make an actual histogram without all the actual data, we use a curve to represent what the data could look like. So for example, if I said to you the weights of humpback whales were skewed to the right. So now see, I'm using a curve to just kind of represent what that distribution could look like. And this would tell me that very few humpback whales were very, very heavy, and most humpback whales were centered down here around some particular value. Again, and I would understand all this through research. Now, we still have a mean, a standard deviation, a proportion, but we use different symbols here. So the mean of a population, we use the symbol mu. It's a Greek letter pronounced mu, but the symbol is kind of like a U with a long tail in the front. And the standard deviation of a population is sigma. Sigma is like a cursive O with a little bit of a long tail at the top, or whatever you want to call that, right? And then a population proportion, the proportion of all people that love chocolate milk would be just P, not P hat. P hat means it's from a sample. We're talking the true proportion, the true P for all people. And again, there's no way you're ever going to know these 3 values because you don't actually calculate it. It's more theorized from lots and lots of research. So that's the difference between a statistic and a parameter. All right, so now let's get back to normal, right? What does it mean to be normal? Well, we talked about this already in a previous video, but some sets of data could be described as, hey, that kind of looks normally distributed. Well, this means that you're mound-shaped, unimodal, and symmetric. To use that phrase normal, you got to meet all 3 of those criteria: mound-shaped, unimodal, and symmetric. So if you feel that a population might look this way, we can model this population with a normal model. And again, instead of a sharp histogram being mound-shaped, unimodal, symmetric, we're going to use this curve like that. Mound-shaped, symmetric, unimodal, boom, that's the normal model. And we describe a population with this along with mu, the standard mean, and sigma, the standard deviation. So we're not going to use X bar and S here because remember, those are statistics from an actual sample of data. Now we're modeling populations where we actually don't have all the data for the entire population in front of us. So we're not actually using statistics here, which is why we're giving it this new name parameters. So here is that normal model, right? Mound-shaped, symmetric, unimodal. We love the normal model. Now, a normal model is completely defined by its mean and its standard deviation. But let's make sure you understand what it means to be normal, right? What it means to be normal is that you have this hump, right? So, what it means to be normal is that whatever your mean is falls exactly in the center, and a large amount of data is near that, right? So if you think of this entire curve, beginning to end is 100% of your population. Your entire population is in this curve somewhere, right? Well, a huge chunk of it is going to be really, really close to the mean. I mean, just look at this huge chunk of data really, really close to the mean. Now, there is some data that's pretty high above the mean, but that's very rare, right? There's not a whole lot of data there, right? There's not very much underneath those values. And there is some data down here that's kind of small, but again, not a whole lot. It's pretty small down there. And that's what it means to be normal, right? It means that you have a little bit on the bottom, a little bit at the top, but most is centered right in the middle near the mean. So let's talk a little bit more specifically about what I said earlier, the fact that, it is entirely created by your mean and your standard deviation, right? So your mean is right smack dab in the middle. So we kind of center that at 0, right? Because if we measure things in terms of how far it is from the mean, well, the mean is 0 from the mean. And then we go up 1 standard deviation and down 1 standard deviation. So this marks a big chunk of data, right? Remember we talked about that when we first introduced you to standard deviation, is that there is a big chunk of data, a large majority of data from -1 to +1 standard deviations. And then we go down 2 standard deviations and up 2 standard deviations. And then we even go up 3 and down 3. Now, why don't we go more than that? Well, as you're going to learn in this video, more than that is actually very, very unlikely. It's very unlikely. Most data is within 1. So anything above 3 is going to be, I don't want to use the word impossible, but very, very, very unlikely. So if you want like a more specific example here, let's give you that. Let's just say that the average weight of an apple is 340 grams. And we know that apples typically follow the normal distribution, with a lot of apples are going to be very close to that mean and very few on the low end and very few on the high end. And the standard deviation of the apples is 20 grams. Okay, so now we could draw this and we could actually label this. So right smack dab in the middle is going to be 340 grams. Then we're going to go up 1 standard deviation. That takes me to 360. We're going to go down 1 standard deviation. That takes me to 320. Then we can go up 2 standard deviations. That's 380. 20, 20, right? Then we could go down 2, that's 300. And then we'll go up 3 and down 3, so that's going to take me up to 400 and down to 280. So, yes, could an apple weigh less or more? Sure, I guess, but it would be very, very unlikely. So this is how a normal distribution is entirely dependent on these 2 numbers. With these 2 numbers, you could draw it, you could label it, and you can get a good feel. So remember, we talked extensively about standard deviation. Within 1, up 1, down 1, is where we have a huge chunk of our data. Many, many, many apples. Look at the area there. There's lots of data there. A large proportion of apples fall within that range. In fact, we have this rule. This is actually a pretty cool rule that statisticians have found through, again, years and years of development and research. They found what's called the empirical rule. And this rule states that between 1 standard deviation below and 1 standard deviation above is 68% of population data. So 68% of a population, as long as it follows the normal distribution, is within 1 standard deviation. And then we expand that to 95% of a population is within 2, -2 to +2 standard deviations. And we see that in blue there. And then finally, 99.7% of a population will be within 3 standard deviations. And that is exactly why we don't go past 3 or below -3, because very, very minute proportion of data will fall outside of that, right? So think about, like, let's talk about how rare that is, right? 99.7% means that only 0.3% is left out. And because of the very symmetric normal model, right, that means 0.15% is above 3 and 0.15% is below 3. So that's just so unlikely, so rare, right? That's 0.0015 as a decimal. It's very, very low. So 99.7, virtually all of a population will be within that 3 mark, and that's exactly why we don't go much further. So this is a very useful model because many variables, quantitative variables, can be modeled by this normal distribution. All right? This is just like literally a short list of the things that could follow a normal distribution. The height of teenage girls, the weights of Roma tomatoes, tread life of a tire, the cholesterol level of 14-year-old boys, gas mileage of cars, the battery length or the battery life of AA batteries. All of these follow that same setup, right? Most of the population of teenage girls are going to be near the mean height. Very few super tall, very few super short. Tires, right? The tread life of tires. How long until your tire tread is gone, right? You need new tires. You know, maybe it's a 40,000 mile average. So most are going to be right around 40,000 miles. Some could be a little high, a little low, but there's not going to be too many that are going to go past 60, 80, 100,000 miles, right? Same thing with the bottom half. There's not going to be too many tires that only last 5,000 miles, right? It's going to follow that normal model, all right? So lots of variables follow the normal model, which is why it's so famous. And, you know, think about it. What this model shows for those variables is that they're pretty consistent to the mean, meaning most data is near the mean. All right, the normal model truly, truly is awesome. It provides a great way to understand the distribution of a data set, and it allows us to have an even better way to predict or model a population value, right? A population distribution. So because it's so awesome, because it's so common, it's actually very predictable. And what is even better is that with the mean and standard deviation of a population, we could see where any one particular value falls. We call this a standardized score. This is actually a pretty big term in statistics. A standardized score is a way to measure exactly where you fall in a set of data. All right? It is a score that allows you to see exactly where a particular value's position is. Now, there's a couple different types of standardized score, but the most famous standardized score is, drumroll please, a Z-score. And I'm not really quite sure, to be quite honest, why we call it a Z-score. What I like to say is it's because it's a standardized score, right? And we couldn't call it an S-score because we're already using S for standard deviation, so we went with Z. Wait, maybe I'm completely off base on that, but who cares? But a Z-score is a standardized score. And there's other standardized score. This is just the most famous. And a Z-score, and this is what you need to study, this is what you need to remember, measures how many standard deviations a value is from the mean. So it puts a number, not in terms of its value, it puts it in terms of standard deviations from the mean. You know, if I'm taking a test, and there's, 100 other kids in my school taking that same test, and I get an 86. Okay. Just knowing that I got an 86 tells me nothing about my position amongst my peers. Am I at the high end? Am I at the bottom? Am I in the middle? Where am I positioned at? So if you calculate my Z-score, you're actually calculating how many standard deviations I fall from the mean. So the formula is actually quite simple for a Z-score. And we just use a Z for Z-score. You simply take your individual value, that's what that little I stands for, your individual value. You subtract the mean, and you divide by the standard deviation. In symbols, that's x minus mu divided by sigma. And this actually tells you where you're positioned. First off, you're either going to be positive or negative. You're either going to be above the mean or below the mean. And then the numerical value will actually tell you exactly how far above or below the mean you are. So let's just say I'm taking that test and I got that 86, right? But the mean for the entire population was something like an 80, and the standard deviation for the entire population was 1. Okay, so that means my z-score is going to be 86 minus 81, all divided by 1. Well, that's going to be 5 divided by 1, which is 5. Now, that's an unbelievable z-score. That means that I was 5 standard deviations above the mean. Now, if you go back to our pictures, we don't even go that high. That's how crazy unbelievable that is, right? So that would actually tell me that I didn't just do awesome on that test. I killed that test. I did fantastic because that's how high I was. Now, I'm not going to lie to you. A score of a 5, I already mentioned earlier, is very, very unlikely. But the point is that, just knowing I got an 86 means nothing. So if the class average was an 81 and the class only deviated by 1, that means most kids are like an 80 to an 82. That's where most kids are. So me being at an 86 is way far above. Now, z-scores have no units. The units on a z-score literally is standard deviations from the mean. Now, you don't have to write that out. You just say the z-score is 5, but you need to know what that 5 represents, right? Now, the cool thing, in my opinion, the best thing about a z-score is it's like a universal measuring tool. We can compare and analyze anything in terms of a z-score. So if we're talking about apples versus oranges, for example, you could say, well, is that apple or that orange bigger? Well, that's not a fair comparison at all because apples are apples, oranges are oranges. But if you find the z-score for that apple and the z-score for that orange, well, then you could get a really good feeling for which is the bigger of the two fruits, because you're actually comparing it to the mean of all of that fruit. So when we go back to our normal model, right? If we think about this for a second, the value in the middle is the mean, right? The mean is going to have a z-score of 0. Because when you use the z-score formula and you take the mean minus the mean divided by the standard deviation, you're going to get a big fat 0, right? And then this value represents 1 standard deviation above. This represents 2 standard deviations above, and this represents 3 standard deviations above. And a standard deviation above or below the mean is a z-score. So these are actually z-scores, 1 above, 2 above, 3 above. And then we could go 1 below, 2 below, or 3 below. So these are actual z-scores, right? This is how far you are from the mean. So let's go back and talk about those apples that we mentioned earlier, right? We said that apples had an average of 340 grams. Then we went up to 360, 380, and 400. And then we went down to 320, 300, and 180, right? So in an apple that is 2 standard deviations below would weigh 300 grams. An apple that was 3 standard deviations above would weigh 400 grams. So let's just say that I'm a little apple, and as a little apple, or I think I'm little, I'm not really sure, I'm an apple, and I know that I weigh 372 grams. And I want to know, am I a big apple? Am I a small apple? Am I just a normal apple? Where am I? Well, all I got to do is find the z-score for that apple. So we're going to take 372 minus the mean of 340 and divide it by the standard deviation of 20 and go ahead and calculate that. I will say this, when you calculate this, please do the top first. So do 372 minus 340, hit enter, and then divide. I'll get kids that do it all in one line on their calculator, and they don't follow order of operations, and they get a very wrong answer. So hit enter first, then divide by 20. That's a z-score of 1.6, okay? So that means that I fall right about here, right? Here's 1, here's 2, 1.6 would be right about there. So what does that tell me? That tells me that I'm A, positive, meaning I'm above the average apple. All right, so I'm kind of big, right? And I'm actually pretty high above, right? Most apples are going to fall from -1 to 1. I'm not like most apples. I'm above that. I'm a pretty big apple. So that's why a z-score really gives you, or the apple, a really strong indication of where it's at on this scale, right? And you can kind of get a nice feel for what's big, what's small, what's pretty typical versus what's kind of weird, right? If you were to find me an apple that falls way out here, somewhere above 3 standard deviations, that'd be a z-score above 3. Well, yeah, that's going to be a pretty big apple, right? That's going to be surprisingly big. You might want to enter that into the fair for the biggest apple of the year, something like that. Those things are very unlikely, where apples in this middle area are, well, Just another apple. So, that's what the power of z-scores could do for us, okay? So keep in mind, if a population is normal, a large percentage of data, 68%, is going to fall between a z-score of -1 to 1. Most data, 95%, is going to be between -2 and 2 standard deviations. And virtually all of a population, almost all, but not all, 99.7% will have a z-score between -3 and 3. So if a value has a z-score smaller than -3 or larger than 3, it's a very unusual, very unlikely, and I would call that a significant value. Again, if you have an apple above 3 standard deviations above the mean, that's a significant apple. I mean, that's pretty shocking. So the normal model is also so standard that we can use technology to find proportions of data values located on a given interval of a normally distributed random variable. So I'm going to save how to do that and what that's all about for the part 2 of this video. So this was part 1, so hopefully it gave you a good understanding of what the normal model is and how powerful the normal model can be in helping us understand data and where data falls. All right, don't forget to watch part 2. It's equally as important.